Recording, and I will share my screen. Is the audio working now? And can you see my screen? No? Test, 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 test. Why are we only two students today? Too early. Yeah. Yeah, I agree. It's a bit early to start, but I would expect. Okay, now we are 3 students. Uh, well, uh, yeah, that might, yeah. Well, they must keep up to date. By the way, did everyone lose access to Canvas or something like that? I had reports that there was problem with Canvas, and also now I can't find anyone in this. Is it just for this course or other courses as well? The Canvas issue. Because I know that they did some changes with the exams and stuff, so I don't know. Yeah, okay. Okay, I will try to contact someone that maybe knows about what happens. Because maybe you lost also the, mm, or are you still signed up to the course on the student web, or is that also gone? Because at least on my thing I can see your names still. Um, and yeah, there was a question in regard with the. She can't find the Zoom link. Yeah. Oh, I can share it again. The link. Yeah, it should be the same as every time. Every. Yeah, but there was a question with the group finder button, but I don't think that we have such a button anywhere. But we have a channel on the Discord for these things to find a group for the labs, but also if you need help from me or the TAs to find a group, you can just ask and we can try to match you in another group. Um, I don't know how many, if there's a lot of groups approved already. Yeah, okay, I see there's, yeah, we have a lot of groups. Mm. But yeah, if you really prefer to work alone, that's also possible. Just that it will be more work for you. Uh, and yeah, I would suggest to work in pairs of two. Um, and we can help you to find a partner if you just ask us. But anyway, it's important to get started on lab 3 because the deadline is already next Friday. Um, yeah, and I wrote briefly about it in the Discord about the exam or the evaluation, and yeah, it will this semester there will not be a regular written exam. And instead, we will, or you will be asked to write a project report or do a project. And yeah, so far the project will be concerned or revolve around Paxos or this or at least consensus algorithms. But the details will be uh, will be posted probably next month, or so. Um, I will post the details with regarding the project. Yeah. Okay. I see that. Mm, yeah, you're not enrolled to the lecturing, but you're enrolled to the evaluation part. So that's good at least. Uh, the teaching is not so important, I guess, for this course. But yeah, anyway, I will try to write to the exam office since this is something that happened to all of you. Um, but I suspect that it's something happened when they changed the evaluation. Okay. Anyway, now we are 9 people, and so let's get going with this. Um, so yeah, today I will talk about the Paxos algorithm, consensus algorithm, and yeah, these slides here were created by Hein and Lander, and all these slides I already shared them with you in the um, labs or assignments repository on GitHub. So they can be helpful to you when in lab 4 and 5 when you need to um, implement it. Yeah, so this is the inventor or the man who created the Paxos consensus algorithm, Leslie Lamport, and also LaTeX he did contributions to. And if you want to read more about him, you can. This is not a history course, so we'll go to the next slide. And this is just to show you that there is uh, hundreds of different research papers regarding Paxos with all types of different optimizations cheap Paxos, fast Paxos, vertical Paxos, you name it. There's been a lot of research going into this, and this is um, uh, like what you now how it looks like that we will create your project, that you will need to look into these different optimizations of Paxos. But today we will just go through um, the basic protocol, the basic Paxos protocol, and also um, we'll go into some improvements or optimizations with multi-Paxos, and yeah, later on, the last thing we will look on is like pipeline or and batching of the protocol. But if you remember from the previous lecture, we looked at broadcasting abstractions, and we got to the part with FIFO and causal order broadcast, and we saw from those protocols that we were able to make them work, or they work in such a way that they respected the order of messages when there was one sender. Um, but as soon as there was multiple senders, then there wasn't any guarantee that the commands was processed in order. Um, so Paxos does this, of course, and it it orders all the client requests to all the replicas so that they are executed in the same order. And also, it's a fault-tolerant protocol, meaning that um, it accepts or tolerates some number of failures of the replicas. And what types of failure are we talking about? Always when it's Paxos, when it only says Paxos, this is only crash failures. Um, it's not Byzantine type failures we are discussing here. If you saw from the first or the second slide here, there's some optimizations or improvements to make it a Byzantine Paxos, and in this case, it will tolerate Byzantine failures. But for today, we will just focus on the crash stop type process abstraction. So yeah, it's used in many systems, the Paxos protocol itself, but maybe more importantly, it's used as a kind of baseline for different consensus algorithms, and it's kind of a go-to consensus algorithm that people will try to relate to when they are discussing new consensus algorithms. So that's why I think it's important to know how it works in detail. One very important property that Paxos has is that it's always safe, meaning that it will never violate the constraints or do something that it's not supposed to. So even if we have too many faulty processes, it is still safe. It's just that when we have too many faulty processes, it will not be live any longer. Meaning that if there's too many processes that's faulty, nothing will happen in the system. Yeah, the plan today is to explain Paxos in like a step-by-step manual that we will go from the most easy case until we have developed the full protocol. And I also linked a paper to you from Leslie Danforth where he um, discusses Paxos, and that paper is kind of more abstract than what we will see today, but still I would recommend that you try to read that paper for your own understanding. Um, yes. So we will start from the most simple case here. We have a single server and two clients, and here the C means a client, S is a server, M is a message, and this sigma, this is a command that's command response from the server, and the subscript, meaning this one that you see here, this means what server sent the message, and on the top we see 2.1 here. This is the messages that was delivered. So when you see 2.1 here, it means that from this server 1 perspective, he first processed message 2. Afterwards, he did message 1, and then he sent the reply. But for the client 2, he got the reply before message 1 was processed. Thus, he in his reply, he only see message number 2 was already processed. And by the way, please, if there's anything that's not clear or you have any questions, you can stop me anytime because maybe I can skip some details too fast. Yeah. So here's this. Yeah, here's the text for what I just explained. So the main thing that we need to think about, also from the last lecture with the causal broadcast, is the things that things must happen in order. So when message M2 is processed before M1, all the servers in the system must do the same order, and also all the clients must do the same or see the same order of messages, meaning that they will get the same result. So what is often done to sort of simplify this kind of is that to show that one message is a prefix of the other one, so that well, in this case it's very simple, that because 2 is a prefix of 2.1 if you consider them as a string, like there's a string with just the number 2, and that's a prefix of a string with 2.1. So yeah. So yeah, in this case we have only one server, and obviously we cannot tolerate any crashes from this one server. So we will need to add more servers. But yeah, we have some constraints or assumptions about their systems. I mean that this is an asynchronous environment with unreliable communication. So messages, they can be take a long time to be delivered. like for example, the network is very slow, or some routing problems, or the messages may be duplicated or lost. It's also a possibility. And we don't have any in our examples here. We don't have any bounds on processing or time delays. Yeah. So when we add the one server, if we are kind of lucky, we can say that now we can tolerate one crash, because now we have two servers and they do the same thing. And if we have like a nice execution like this, we can see that yes, if number one, number two would crash, the other one will have the same state, because in this toy example here, they are magically executing the commands at the same time. And also they are receiving the messages from the client in the same order. So this is kind of a dream scenario, but in the real world, such a protocol will not be sufficient, because messages from the client can be come out of order, or the client can decide he will just send his message to one of the servers, and he will send a different message to the other server, or the one server can crash in the middle of execution and stuff like this. So we cannot. This example is not sufficient. But one thing to note from this figure is that in all the examples we will discuss today, we are always talking about deterministic execution, meaning that given the same input, the servers will produce the same result. So this M1 processing from server 1 and server 2, they will produce the exact same result. So that the processes cannot be something random. It will not work. So here is one execution scenario where it's clear to see that we cannot simply add another server like that, because in this case server 2 is processing first message 2 and then message number 1, but server 1 is doing first message number 1 and then afterwards message number 2. And this is due to the client is delaying, or maybe it wasn't the client's fault, just the network was slow. Anyway, his message was received to the one server much later than to the other server. So again, we can see that the prefixes of these responses that the client receives is not, or they're not prefixed of each other, so that it's clear to see that they are not in the same state. So we will start to create this Paxos protocol by ordering the client request. And how can we do that? The most usual way is to designate one process as the leader. We looked into leader detection and leader election algorithms. And in this scenario here, we see that server 2 will only start processing the message M2 after he received an accept message from server 1. So we have server 1 acting as leader, and server 2 will just follow server 1's lead. So only after server 2 tells, after server 1 sends the accept message, server 2 will do the processing. So this means that even if the client 2 sent this message very late, or it was delayed to server 1, it's still server 1 that coordinates everything to make sure the processes are executed in order. But we didn't completely solve the problem, because we can, even though now we are kind of protected from clients' messages being delayed or reordered, accept messages from server 1 can be reordered in the same way. So with this very simple protocol, if the accept message was delayed, we would still end up in the scenario that I explained before, that now the execution order is different from the two servers. So to solve this, we can just put a sequence number, for example, an integer, attached to the message, meaning that server 1 say now accept message 2 as with sequence number 1, and when yeah, I guess this should be this slide. So what the server number 2 will do is that when he receives the accept message with a higher sequence number than what he already and then what he's expecting, he can just discard this thing. Because server 1, he is still waiting for his first message. So only after he can process message 2, he will consider the next message. So in the this scenario here, we have now ensured that the server 2's processing is a prefix of server 1. That even though server 2 received the message M1, he doesn't do anything with this, because he's waiting for accept from the leader, and when he gets an accept from the leader, the first accept he gets, it's not with the sequence number that he expects, so he discards this, and he waits until he gets the accept with the sequence number he was expecting, and only then he will reply back to the client. So in this scenario, we have an issue with where's my that server 2 didn't execute M1. Okay. So what can we do about that? We can do a buffer type thing, but is it a good solution? Maybe not. Usually, what people do is that they do what shouldn't say people, what protocols do is to have a retransmission mechanism. And yeah, so because a buffer, it has issues that it might be filled, for example. It requires or it can require a lot of memory on the replicas and other issues. But anyway, the Paxos protocol uses retransmissions. So that if after an accept message, the leader expects a learn message in reply, kind of like an acknowledgement in this case. So in this execution here, the leader is trying to get to send the accept for message 1. It's trying to send the accept for message 2 with sequence number 1. That accept message is lost, and after some time period, he sends the accept message again, and this time the server 2 replies back with the learn, and then he executes message 2. So now with this scenario here, we have achieved that M1, no, S1 and S2 are executing the messages in order. Both have M1, M2, M1, and M2, M1, both of them. And yeah, you can see the sequence flow with the clients also. And yeah, you see that both replicas have executed the in order. So you know about what the leader does is the leader of the what did the learn message? Okay, we have a question. What did the learn message do? So the learn message, this is so you can, if you think about the accept message here, this is to order the client request. So the accept message, they are used to create some order to the requests with the sequence number, for example, 1 and 2. And then we add the learn message as part of the retransmission mechanism. So the accept message is sent, and the leader keeps trying to send the same accept message until he receives back a learn, so that when the leader receives the learn message, he knows that he can stop retransmitting the accept message, because now the other replica says that he knows, he learned about this message. So if the other replica says that, okay, now I learned that message 2 should be processed next, then he can be kind of sure that that's the state of server 2. So the accept message is used for ordering the requests, and the learn is used in the retransmission protocol. I hope it was clear that. Yeah, and yeah, I guess it says here retransmission mechanism. Leader only sends next except when he get learned from so to so. This text that I have highlighted here, this is the learn message, and the other things are this is the accept message. So far now we have only introduced two new types of messages: the accept and the learn. Was it clear? Okay. So now we will talk about because now we solved the issue with reordering. So that now we have made some assurance that all the replicas are executing in the same order. But what we wanted initially is that we wanted to be fault tolerant. We wanted to handle failures. So what can we do when, for example, the lead are crashed? As you saw when we talked about lead detection, and probably from lab 3 already, what should happen is that once this crash is detected, then another replica should take over and execute the message. But there is some nuances to this that we have to now think about when does it crash. In this case, it crashed after sending the accept, and of course it should be drawn with a learn message here, but it's not. And it crashed, and then the next server took over and executed the next message. So it's also possible to have this scenario that it didn't execute anything and crashed, or it can execute nothing but trying to send the except for one message, and in another it can have executed the message before it crashed. And the worst case that we need to really avoid is this case here, because now it has replied given one response to client 1, and the other replica didn't learn about this message, and another client is communicating with it. So this type of execution, it's easy to realize that this is a problem if you think about locking or specifically like deadlocks. If this message here was, for example, a request to get the lock on some resource, for example, a hard drive or something like that, then now both clients believe that they should have the lock, and well, server 2 believes that client 1 should get the lock, but client 1 already received the lock. So we don't want this type of scenario. Yeah, just the locking. So what we do is just to because if you remember from way back when we discussed the learn protocol, we kind of just executed the message when we got it. But to solve the issue with the clients receiving different commands, different results, we need to wait until we have received the learn before executing the message ourselves. So instead of executing M1 directly when we receive this request, we simply wait until we receive the learn. Yeah. So yeah. Now when we change the leader, we know that everything that the leader has executed, we have also executed. Yeah. So this is why now that the sigma it has the superscript 1 2 because server 2 it also did the process M1. So in this type of scenario, we will not have the deadlocking issue. And yeah, so yeah, like you will see in the labs 3, then you also need to think about this case. It's something many students can forget about, that we also want to check that the leader election algorithm doesn't do anything, or it stays it remains as the leader if another replica crashes. So yeah, this type of execution flow can be useful to you when you're developing yourself. But yeah, so we see that we still have the prefix of the message. Like the client 1 has the sigma 1 1 here is a prefix of sigma 1 2. Yeah. So what we did, we started with a single server, then we added first the accept message to auto the client request, and then we added the transmission mechanism with the learns, but we saw that there is or can be an issue with leaders replying and then crashing without ensuring that the different replicas saw this message. So we implemented the wait for learn protocol, and this protocol simply moved the execution from doing it immediately when the leader is sending accept, and then moved it to only execute after we receive learns from the replicas. Yeah. So the we saw or we will see that also the learn message can be lost here. But if a learn is lost, this is kind of the same thing from the point of view from server one that the accept is lost. So he will keep trying to retransmit because server one, he doesn't know that his message was received. So it doesn't really matter from the point of view of server one if the accept message is lost or the learn message is lost from the other replica. The only difference is here that we have kind of the protocol where server 2 is executing M1 and then afterwards receiving a new acknowledgement. So he will not execute again here. This is an important thing to see here, that server 2 doesn't execute the message without checking the sequence number. So the server 2 will check that he didn't see the sequence number earlier, and only then execute it and send the learn back. Okay, any questions? If not, we will go into more difficult. Oh, it's not really more difficult. But is everything nice and simple? Nice and okay. Yeah. 5-minute break is requested. Yes, let's take a 5-minute break. It's okay. Let's continue 10 minutes past 9. All right, all right. I hope you're all ready. So, by the way, next week we will plan to offer labs at the campus if anyone is interested in attending the labs at the campus. But yeah, I think we still need to do or support the remote assistance anyway. But yeah, on Mondays and Fridays it's possible to meet at the campus to get assistance with the labs from Rodrigo and Bahid. Yeah. Okay, let's jump into the Paxos. So, yes, what will we do now? We will no longer have the assumption that the failure detector is perfect or accurate, and realize that in asynchronous environment we can have false detections or detections can be slow. So um, a network partition, it looks like this in the illustration. And well, sometimes everyone forgets to explain what is a network partition, but it's kind of like you don't lose your let's say internet connection, but there is one link or a few links that's broken between larger clusters, so that both sides kind of believe that they are connected, but between these two clusters there is a broken connection, and in this case we can call it a network partition. Yeah, so in this example here, what's the problem? Well, the problem is that both S1 and S2 believes that he is the leader at some point, and he is executing the client's command. For example, S1, he tries to send the acknowledgement and he doesn't get a reply. And then finally his leader detection or failure detection algorithm kicks in and he say, you know what, this other replica has crashed. I'm the only server left and I should just reply back. And the same thing server 2 does, that he's believes that server 1 is the leader, but he doesn't do anything. And only finally after his failure detector kicks in also, he now takes over as the leader. And yeah, he executes the command. So suddenly now it seems like we are back to the old scenario where the clients are receiving different results. So what to do about this? Or when the network partition resolves, can we, for example, roll back on the client, meaning that the client can just send whatever message they had received, and then we will try to rebuild the state based on that. Um, but usually relying on clients, this is not a viable solution because clients, they maybe, for example, they logged off or they don't want to follow the protocol. Many issues. So we want to avoid relying on clients, and what what's done is to simply add another replica, and now we must remember what we saw before with quorums or the majority. So when we have now added another server, it's possible to have a majority of them. So 1 and 2 is a majority, 1 and 3 is another majority, and 2 and 3 is another majority. So in any number of processes over a half, and also 1 to 3 is a majority. So any set of processes over half is a majority. Because remember, this is a crash stop process abstraction. So we need 2f plus 1 processes to tolerate f failures. So in this scenario, even if S3 receives commands here, he doesn't have a majority, so he will not take over as the leader. And accept messages and learn messages are exchanged between the two correct processes. So there's another scenario here where the leader, there's a leader takeover, and the S2 will take over as the leader because he has a majority with together with S3, so that they can reply back message to the client too. So yeah. So here we can see one thing here, that S1 processes M2, and so does M2. Yeah. S1 processes M1, and S2 processes M1 without waiting for server 3, because just 1 and 2, so 1 and 2, they have a majority together, and they don't need to wait for server 3. But server 3 needs to wait from for the acknowledgement from server 1 before he can process. And yes, with the client request. So yeah, to deal with the network partitions, we added another server, and we added the wait for learn protocol to not run into the issue where clients are receiving different commands, and the servers are in different states. And we saw one example from why that can be bad with the locking example. And well, and yeah, the leader he waits for one learn before executing the request. Yeah, so still the protocol is not perfect, because we can have both a network partition and a crash at the same time. Or yeah. So in this case, we will end up in an undecided state. That we have the scenario where leader S1 is sending an acknowledgement for message 1. Yeah, it doesn't arrive to server 2, but it relies, no, it arrives to server 3, but very late. And also it arrives so late that it's after server 2 is being designated as the new leader, and that has sent a different message M2. So now the question is, what will S3 do? Will it yes, process the message M1, or is M2 the correct message? Yeah, and then afterwards it crashes. So for example, in this example here, it takes M1, tries to send a learn, which is not successful because of the network position. But anyway, he S3 knows that a majority of the network knows about this M1, meaning S1 and S2 knows about M1. So he think, okay, it's safe to execute. He can reply to the client, and afterwards he crashes. Or different scenario is that, yeah, he didn't actually receive this message, and he instead received the M2. He does the processing of M2 and sends back to the client. And also in this case, he crashes. So, well, the server 3 crashed, and as we saw, he can have executed either one M1 or M2, but this is undecided, and yeah, we really don't want such a scenario, because now we don't know what messages the client has already received. And as you remember, we have this design philosophy that we don't want to rely on the clients. We don't want to make the client somehow tell to us what messages did they receive from before. So the realization is that this um, this problem arises due to false detection of leader change, because we detect that S1 was crashed, but yeah, in let's see, in this scenario here, if you remember, we S2 changed the leader after the timeout because he thought that S1 was crashed, but as we see, it is not the case that S1 crashed. Only there's a network condition and the timeout incurred. So this is kind of the root of the problem, that now you have two processes that think they are the leader. So yeah, we can solve this with what they call a explicit leader takeover protocol, and it's basically like this. We add another communication step with a prepare and promise message. So yeah, I guess we will see soon, but here the S2 sends a prepare message to well, to everyone in the system, and they reply back with a promise message. So the idea here is that the prepare, it's saying that you know, I want to be the leader now, and the promise message, it's saying that okay, I promise to you that you are my leader. This is how you can imagine these two messages, and they've afterwards follow the messages that we saw from before with the accept and learn. So yeah, and if the S1 is now trying to send accept, we can ignore this because we have now promised to server 2 that he is our leader. So we have a explicit leader change here with the prepare and promise protocol. So yeah, we have one issue here, or one undecided event now. What if the different or the replica 2 crashes? Then who will be the next leader? So either the server 3 can send a prepare and receive a promise from S1 and become the leader, or yeah, server 1 can try to send a prepare and wait for a promise back. But the way that the protocol and Paxos makes this fair is that instead of sending the server identifier, only a identifier is sent, or a round number. So here he is sending server 2 is sending round number 2, and later on server 1 is sending round number 4. And the general rule in this type of algorithm is that you always will trust or respect the higher round numbers. So if you saw round number 5 already, then any message with a higher round than 5, you will be respected, but any message with 5 or below, you can ignore them. So this is obviously a crash, not a non-Byzantine type protocol. And in the typical implementation of Paxos, and you will do this in your lab, most likely, is that you just use like a modulus operator, so that any number where the remainder is 1, like if you do 3, now if you divide by 3, you will get a remainder. So for example, you do 7, you divide by 3. This is like 2,333, but it has 1 remainder. So since it has 1 remainder, server 1 will become the leader. And similar with server 2, 8 divided by 3, it has 2 remainder. And 9 divided by 3, it has 0 remainder. And this is just the typical rule that you will follow, so that you can just increment this sequence number without having to do some fancy arithmetic for that. Yes. So far this is the messages that we have discussed: accept, learn, and now the 2 new ones: prepare and promise. And let's see how this can all work together. Now we see that this is the full protocol. First, the S1 tries to send the acknowledgement. This is doesn't arrive to server 2 because of the network partition. There's a timeout that has elapsed. The S2 detects the timeout, and he sends a prepare message because now he wants to become the leader, but he needs to have some confidence or some majority that other processes will consider him as the leader. So he sends to server 3. Server 3 replies back with a promise. Only then server 2 will detect that he is the leader, and then he can send the accept. Server 3 replies back with the promise, and they execute the message and replies to the client. And in the middle of this, the acknowledge from the server 1 arrived at server 3, but this is now ignored because server 1 is sending something from round number 1, but server 3, he already learned about round number 2, so he will discard that message. So the problem that we wanted to solve or to make some conclusions about this scenario that we just saw. And well, actually we didn't I guess this is kind of the same slide. Yeah, we kind of don't know yet, even now yet, we didn't completely solve this issue because we don't know if server 3 crashed before he processed the server and the message 2 or after, or if his reply to the client was broken also. So actually now we don't know where he crashed, and thus we cannot say that server 2 and number 1, they know about the state of server 3 before he crashed. But we know kind of that he has sent a promise for M2, so he cannot have processed M1, and we know that yeah, he crashed, and the correct thing to do now is, since that we know that he learned about we have the leader decides the order in the round number 2, and thus we can even if we don't know if server 3 already crashed, we can assume that he did execute this M2. So yes. So we can yeah, then we will see what happens if the M1 here is actually received before the network partition is established here. So in this case, we S3 learns about M1. He tries to reply with back with a reply. He does a processed message, and he is able to reply back to the client. Now the server 2 detects that he wants to become the leader. He does the prepare and promise messages, and he is elected as the new leader. And yeah, then later on server 3 crashed, but server 3 he processed message M1, but he never told anyone about this. So when he crashes, neither server 1 or server 2 knows that he did this. So how can we solve this issue? We need to just tell the server 2 about this in the promise message. So since he received an accept for M1, he can process it, and then he will attach this when he sees a round number 2. He will in his promise response, he will include the messages that he saw previously. So this is pretty similar to the FIFO other broadcasts that we saw before, meaning that you kind of append old messages to the new ones, or to, yeah, in this case, the promise message. So yeah, yeah, we tell the new leader about the accepted messages. Then M2 sends the acknowledgement, and yeah, we don't need, we'll do a no up operation, or we will do no operation just because we have already executed M1, so we don't need to execute it again. But now we have just one issue here, is that S2 didn't receive a majority for M1 because the learn didn't arrive back. So he, like we discussed some slides ago, is that he continues. He continues sending the acknowledgement messages, and after the network partition is solved, he is able to communicate with S1, and then they can process M1. So yeah, I think this figure should, like this S1, he will not think that he is the leader. Will be correct, but don't worry about that. Yeah. And if we have we can have a different scenario where the server 2 crashes after becoming the leader, and it's server 3 that wants to take over the leadership. When he sends the prepare, he gets the promise with the reply back from the server 1 with the message that server 1 accepted. So now we have basically reached the end of where we have the Paxos, that this is the message flow in Paxos, and yeah, we will see what happens with more failures. But is there any questions so far? Like now we saw that we can have one failure and we will still be safe, and also with the network partition and the concurrent failure, we will also be safe. And what we did is that when there's a leader change, we added this prepare and promise protocols, and also we appended information about previous accept messages in the promise. Okay, no questions. So let's blast on through. Yeah, we saw we can deal with one crash but what if there's two crashes? Uh, we three servers can not tolerate two crashes. It can only tolerate one crash, and the rule is this 2f plus 1. So we need first we say how many faulty processes that we want to tolerate, and after we do this, we calculate this number. So if we want to have tolerate three failures, we do 2 multiplication 3 plus 1. This is 7, and with 7 replicas, we can tolerate 3 failures. So a majority in a 7 scenario, 7 replica scenario, this is 4. So f is 3 plus 1 is 4. So I guess this is clear. So an example with 5 servers. It can look like this. There's this one thing that we kind of get away with 3 servers, and that's that in the 3 server case, it's sufficient that the leader receives one learn message, because when he has received one learn message, he has a majority because he sends a learn to himself and he receives a learn from a different process, and then he can continue. But in the case of 5 servers, you need not only one, but you need two, because you get 2 from different processes and plus your own, and this is 3 total. Yeah. Need to drink. Mm. Yeah, and then maybe I forgot to mention this. This is also the case for different replicas. That replica S2, he has got accept from the leader, plus he is sending learn to himself, and in the case where we have only 3 replicas, he now believes he has a quorum. But when we have 5 replicas, we cannot do that. We need to get learned from the different replicas as well. So most common is 2 ways to do this: all-to-all message exchange, or have another communication step with a commit phase. So yeah, you can implement either of these in the lab, I think. Most commonly, people will do the all-to-all, and yeah, it looks like this. That when you are sending a learn, you are not sending the learn only to the leader, but you're actually sending the learn to all the other processes. And when you get a majority of learn, you can continue to execute the message. So yeah, the different protocol is to send the learn only to the leader, and he will create a special commit message which you can then receive, and after this you can do the processing of the message. So that's pretty much it about the first part of Paxos. So yeah, we have a message flow here, how it can look like with the most commonly, like we will implement in lab 5, 4, lab 4, I guess. That there's a message from the client, and the server is sending a accept message, and then learn messages are exchanged. And when there's a quorum, the M2 is processed, and the same thing goes when there's a message M1. So one thing to think about that we will see later in the next slides is that the multi-Paxos, or in the basic Paxos, it's only for one message. So whenever people are talking about the pure Paxos protocol, this is only to decide the one message, to have consensus of one message. And when we want to have multiple message, we call this multi-Paxos. And yeah, so this is the message flow from Paxos, and I was thinking in the next we can take a break, and afterwards I can explain all the parameters there that's been exchanged, like the round and vround, vval, CI, and different things. Because we are not done yet for today, but yeah, if there's any questions, we can do that now. Otherwise, I suggest we take 10 minutes, and afterwards I will continue with another presentation I have somewhere. So, well, yeah, this it's kind of easy to get lost in the Paxos protocol, so don't be afraid to ask questions, but yeah, maybe it will be more clear in the next slides. So let's take 10 minutes now then, and let's continue. Right, 5 minutes. Last time. Okay, see you in 10 minutes. All right. Let's continue with the next slides here. So this is another presentation regarding Paxos. Kind of have a different view of the thing, more as like implementation. How can you implement these things? It will be more discussed in this presentation. So our goal here is to discuss first the Paxos and then the multi-Paxos protocol, and yeah, this is how it looks like. So here we have still we have server 1, server 2, server 3, and we have now all these bars here, and these bars, they are a consensus instance. So in each slot here, we want to fill with with commands that the server can execute, and the important thing is that they must all execute the same command in each slot. But and we don't care about the order as long as they all respect the order and would have the same order. And on the bottom we have the number 3, 4, 5, 6, etc. And this is the slot number. So in each slot, one command is executed. And yeah, the single in each slot there is a single decree Paxos, as we call it, and remember in the single Paxos, it's also only possible to execute one command. And still we have the 3 replicas, and they are drawn here, 1, 2, 3, and inside each replica there is 3 different symbols, which is the proposer, the acceptor, and the learner. And this is typically the roles that is used when people when the Paxos algorithm is implemented. And in theory, you can run the Paxos roles on different machines. But for example, in your lab, you will run all of these roles on the same machine. So what's inside one such replica? This is the proposer, responsible for the propose message that we saw. We have the acceptor, and then the learner. So first of the proposer, he receives the commands from the client, and he proposes the value to the acceptor. since we will see with the message exchange later on. The acceptor, he chooses the consensus value, and finally the learner learns the consensus value, or he communicates with the client. So remember, our goal is to choose a common value, or a value that's shared. Common value that's shared for all the replicas, and typically we can interchange the words value or a client command, but it means the same thing. And the main thing is that all the replicas must decide on the same value. So so one thing to think about is that we discussed all these messages from in the previous slide with different messages, and we saw that the first thing we added was the acceptor, so that we can follow the client request, and later on we added the learner to have the rich transmission, and only finally we added the proposer that deals with explicit leader changes. So in the case that the leader is stable, the only or you can say that only for the leader this proposal will do anything. For the other ones, they are not active until this replica is designated the leader. But in some cases there is asynchrony involved, and then there might be multiple processes that think they are the leader. Yes. Asynchrony, you can have more leaders or no leaders also. So this is the agents, proposals, learners, acceptors, and they communicate using these values. So first off, client chooses any value v, sends to the proposer, which is, remember, the leader, and the leader here is leader for one specific round. He will then first kind of send a prepare message, and in this prepare message he attaches this constraint consensus value, and then we have the acceptor, which has three main variables. The round, highest round seen, meaning that if you remember that we tried to solve the issue with um, leaders executing a command and then crashing. So the here we have the round so that we um, um, this represents the highest round that we have seen so far, and also we have the v round and the v val, which is values from something that we accepted in the past, so that we can use these values to reply back to the promise message. And yeah, the learner is simple. He only has the consensus value. Yes, and one thing to just to not be confused about is the word slot and round, because when we are talking about round or ballot, we are talking about the single Paxos, and in the multi-Paxos we have the slot. Yeah. Anyway, yeah, this is the API. So the client sends a message to the proposer. The proposer sends a prepare to the acceptor. The acceptor sends a promise to the proposer. The proposer sends an accept to the acceptor, and the acceptor sends a learn to the learner. And these are the parameters that's attached to the message. So then we will go through the execution. There's no questions. So now we are still talking about the single Paxos case. And we have 3 replicas. So each replica is represented in a row here. So it's like replica 1, replica 2, replica 3. And the circle is the proposer, the square is the acceptor, and then the pyramid symbol. I don't know the name exactly now. It's a learner anyway. It's angled square. Diamond, maybe. Diamond is the good word. Yeah, but first the proposer, he sends the prepare message with the parameter 1 for the round 1, and this message is kind of asking the acceptors to prepare for consensus, or you can maybe also phrase it as that I am the leader in round 1, and if the acceptors agree, they will update the value that we saw with the highest round that they have seen, because now the highest round that acceptors have seen, this is round 1. And they will all reply back with a promise message for round 1, and then they will have a 0 value for the last round that they had a accept message on, and also the value that was in that round, because they don't have anything. So afterwards, the proposer sends the accept message with the value 5 to the acceptors. They all update their variables, saying that now the highest accept message I saw was in round 1 and had the value 5. And they all do this. And afterwards, they do the all-to-all message exchange to the learners with saying that now we have we use the consensus for round number 1 with the value 5. The learners will get a majority of this and update its value. So that's the execution of Paxos. Now we are very happy. Some optimizations, as I mentioned, is that in multi-Paxos, if you have if you can assume that the leader is stable, you can commit to send the prepare and the promise message, because it will be the same leader for multiple instances. This doesn't work when there is a leader change. All right. What I mean by that is that just to be clear, this message here, if you see on the top right corner, it says 1A and 1B. And this phase 1, it can be omitted if you have a stable leader. So you can jump directly to the accept message. And yeah, reply back to the client. So let's see some problems, or let's problematic situations. For example, here we have one replica. Replica number 3 is completely crashed or removed from the system. Since we have a majority, Paxos can still continue working as before. But maybe the more interesting is when we have concurrent leaders. And this means that we have 3 proposals here, and they all have received different client commands, and they all think that they are legal for some reason. So what can happen is that the first replica sends a prepare message, but this message is only received by acceptor 1, acceptor 2, which updates its highest round seen. The prepare message to replica 3 is lost. So only replica 1 and 2 replies back with a promise. And remember, this value is blank because there's nothing that has been accepted for any previous rounds. Yeah, the proposal number 2, he also, remember, thinks that he is the leader, so he also sends a prepare. Now, acceptor number 2, he updates his highest round seen, because before he saw round number 1 was the highest, and 2 is higher than 1, so he updates. And the same thing with acceptor number 3 here, and they reply back with a promise. And well, what can happen is now the accept proposal number 1 sends a accept message for that round with the value that the client suggested or wanted. And now you see an interesting thing that the acceptor one, he um, accepts this message, or he goes along with this message. He updates his values here, but acceptor two, he ignores this one because he sees that the um, round attached to this accept message is lower than what he saw before. So he throws this in the trash. And when the acceptor number one broadcasts his learn message, he's not successful because um, uh, there's no majority here. So each learner only receives one learn message, and they cannot get majority from just one. Yeah. Then remember, everything here is concurrent. The proposal two sends accept message to for the value that the client suggested, but this accept message is only received by acceptor number two. It's lost to the two different acceptors. Acceptor number two will update its values. It has received a accept message for round two with value 76. It also now tries to send the learn, but the same thing happens that means that there is no majority here, only one learn to every learner. And well, finally, then proposal three comes along, and he sends a repair message which reaches acceptor one and acceptor three. So these two acceptors, they will update the highest round that they have seen, and they will what else will they do? Will reply back with a promise message, but now we can see that one promise message contains actually a value. So because acceptor one had already accepted a message or received the accept message in the past, he must include this in the promise message. So we have one promise message with a previous accept message and one without anything. So now the dilemma for proposal number three is that he knows that the value 11 was chosen, or the value 11 have been voted for, or there has been an accept message sent for value 11 in round one, but he has no idea about if acceptor two also did this or not, because he only received promise from the different acceptors. But anyway, he is not discouraged by this. He concludes that all right, I have there is a possibility that the value 11 was chosen by majority, so he will actually send an accept for this message. So see here now that the client actually wanted number 22, but he must actually respect the, the value that's included in his promise message. So he discards the value 22 and updates the value to 11 and includes this in his accept message. Yeah, but this message is not reached to accept the one, but it's reached to the two other ones, and we can see that the acceptor number 2 he updates because around 3 this is higher than 1, and yeah, so those acceptor 3, and now we have a majority here, and this means that this value it will not change now. So it cannot change because there is we have a majority here. So any majority that we can try to make from these 3 acceptors, it must include at least one of these 2. So what does the acceptors do? They send the learn message to the learners, but one learner he doesn't receive anything from acceptor 3, but the 2 other acceptors they receive a majority. So they update their consensus value 11, and now we have concluded the phase 2, because the learners have a consensus for 11. So there's no way that this learner that didn't receive sufficient learns that he can get another value here. He can only get 11, because if you try to send different prepare and promise and accept, these values will not change. Only the value for this one can change, but not okay. Only this value here can be changed, but the value 11 must stay. So yeah. So how can that learner learn about the value? It can request it, for example, or it can request another Paxos round with prepare and promise, because he's waiting for actually the proposal to propose a value. So that was one Paxos instance. So what do you do when you want to have multi-Paxos? Main idea is that you have these slots that we saw before, and inside each slot you run one such consensus instance. And there's two main possible optimizations that you can do and will be asked to do in lab 6, I guess. That's to either pipeline the execution or to batch the execution. So the pipelining approach, it's like that you can start multiple consensus instances without having to wait for the previous one to terminate. So it can look something like this. So and the cool thing is that we can allow that these slots they reach consensus in different orders as long as we have as we actually do the execution of the command with respecting this order. So it's possible that number 5 reaches consensus before number 3, but we will not execute the command in slot 5 before we have executed 3 and 4. So we can like try to get consensus for values, and once we get the consensus, we cannot just wait until we have gotten the full sequence. And well, we cannot allow that we have millions of concurrent instances running concurrently. So there's a parameter alpha. It's typically used to limit this, so that the resource usage, or the resource usage of the system is not too high. So I guess you will have to think about this in lab 6, like what is an appropriate parameter for alpha, and you will hopefully do some evaluation of this. So a different optimization that's possible to do is to not oh no, okay, wait, I will jump a little bit too far. So yeah, there's just one figure here to kind of illustrate the difference between around and the slot. So I don't know, maybe it's not clear to you now what is around, what is a slot, but if there is some specific questions about that, I can answer now. And if not, I suggest that you, when you have to do the actual implementation, you just check this slide, so the previous one, to not get these two mixed up. But around, whenever it's around, or sometimes also it's called the ballot. It's concerning the who is the leader, and when it's a slot, it's like the different consensus value. Consensus instance, I mean, not the consensus value, but the consensus instance. And yeah, the next optimization that you will do or can do in lab 6, it's batching. Everyone knows what's batching. Just bundle a bunch of commands together instead of having very small commands like number 5, number 8, and number 10. You just pack them all together, and you reach consensus on this bigger value, let's say. So there's obviously some disadvantage that you have to wait for the enough plan commands or a timeout, but there's advantage is that you don't need to have so many consensus instances. So the last thing is the algorithm itself, and typically what was expected in this course is that you could explain this algorithm and also write this algorithm by heart, kind of, that if you were asked to say what is the algorithm for the acceptor, we have the acceptor here, then or proposer, then the student was able to come up with some pseudocode. But since you are so lucky that there is not a usual written exam, then I cannot ask you to memorize this. But still, one thing that you will find from this is that this is very, very valuable for yourself when you need to do the implementation in the lab, because the code in Go, it can quickly become large with a lot of function and different Go routines, and they're calling each other, and this goes there and this goes there. So it can be kind of more difficult to get a full overview of what's going on. So whenever you go into that scenario, it can be valuable to go to these algorithms here, because they are very compact, and you can try to reason about where is your implementation stuck. So yeah, and also for the project, it can be useful to relate to this when you or if you are asked to compare different algorithms. But this PDF, they are in the course info. No, not in the course info. I'm sorry, in the lab. So if we go to lab 4 here, it's what's it called here? Yeah, that was something to. And go to the assignments, and yeah, there's this one, lab 4 resources, and there we have put some PDF, and today I think we went through this one, this slide. Yeah, this is one slide. So here you will find the execution flow, and I wonder if we is this one. Reliable, insanely simple, and this one, I guess. Paxos from scratch. Let's check. . yeah. So this one we also saw earlier. This is kind of more, let's say, more discussing the reasoning of the algorithm itself, like starting from the very basic protocol with only one server, and then we add two servers, and then we try to order the requests, and it builds up the Paxos protocol step by step. So that's this slides there, and then the other one, the insanely simple, it's more just jumping into the protocol directly and saying, okay, we need prepare, we need accept messages, and without giving you so much background. But for myself, when I implemented these things, it's very useful to have this type of figures with the message exchange, so that you can really see who is sending what message, and what do they contain. But yeah. So, any questions regarding Paxos, the implementation? I hope that we will publish the lab for lab 4 next week. And yeah, there's also a glossary here. But yeah, we will publish the labs for next week. And now you should try to find a partner for lab 3 to finish it, because in the lab 3 you will create the basis for this lab, or you will use the leader detector that you develop in lab 3 to use in the Paxos implementation. So yeah, I started a bit early today because I thought we needed more time, but I see we still have a lot of time actually. But yeah, so I will try to contact someone with the question that most of you lost access to Canvas and such, and yeah, if anyone needs a partner for the group labs, just yeah, you can try yourself on Discord, or you can ask me or the TAs if they can help you to match up with someone. But try to do it as soon as possible, so you don't fall behind. Okay, any questions? If not, then we will just end and continue our day. Okay, everyone is satisfied. Great. We will continue on Monday, if I'm not mistaken. Just since we have so much time, we can check together. Lecture plan. Yeah, and next on Monday we will go through some different discussions about consensus, and yeah, if you feel that you really know Paxos, then it should be just child's play. But yeah, I think that the best way to understand Paxos is really to start coding, to start doing it in code yourself. But everyone is different. So anyway, That's end for now, and we will continue on Monday. Bye.